Hello, in this video I'm going to describe the hybridization types that you can see in carbon, the element carbon. Carbon has atomic number of 6, so it has 6 protons, and if it's neutral it has 6 electrons, and those 6 electrons can be spread in orbitals in form of electronic configuration as 1s2, 2s2, 2p2, and that can always be written in an energy diagram where the 1s is filled by 2 electrons, 2s is filled by 2 electrons, 2p you first singly fill up before pairing. Now you see that there's an empty orbital here, what I'm suggesting to be pz. So if you promote an electron, these are electrons, these half-barbed arrows are electrons. If you promote it upstairs, you'll be mixing the S and the P. They have different shapes, they have different values, so you would know that you're mixing two different things. So if you promote it upstairs, you're going to get hybrid orbital, just like you'd mix apples and oranges in the blender to make a smoothie. It's the same thing happening here. You're mixing orbitals, so you get a set of mixed orbitals. We call those sp3. They will be degenerate. Degenerate orbitals means that they have the same energy. Just like these p's have same energy, the hybrid orbitals will have same energy, but are higher than s, lower than p, somewhere in the middle. An example is a carbon. Carbon has a valency of 4, so these 4 electrons, when in bonding, they will be in one of these sp3 orbitals. In fact, these single arrows I'm showing here represents these 4 electrons. So if you're trying to make methane, then that means hydrogen has to come and share with the carbon an electron, because an electron is made, a bond is made by 2 electrons. A bond is made by 2 electrons. So if you have to show the Lewis structure of methane, then that's how it will be, where they're sharing that covalent bond, but the carbon electron is really in the sp3s. Okay, so if I'm to draw a cartoon of what's happening, the hydrogen will bring its s, the carbon is bringing its sp3, you're going to make a bond, and that bond is going to be called sp3, sigma bond. Okay, so similarly the same case will happen on the other sides, where those hydrogens are bringing their s's, and then the carbon is bringing its sp3 for overlap. Okay, so the sp3 bonds, sp3 bonds will be formed in between. So let me show the methane now in full and tell you that those single bonds you are seeing right there, those single bonds are the sp3, because the hydrogen gives the s, the carbon gives the sp3. The bond angle is 109.5 roughly for sp3 hybridization. We discussed that in another lesson, and the molecular shape is tetrahedral. How about when you have sp2 hybridization in carbon? Same electronic configuration of a normal carbon element, low energy, we call it ground state. When you promote an electron, then you'll have this piece having single electrons, and the s will be left with 1, but to make sp2, only 2 of the p's having electrons will take part in mixing. So you'll get an s and 2 p's mixing up. We call that sp2. So you'll have 3 of them. We call those 3 electron domains. The other p orbital that did not take part in the hybridization will remain unhybridized. Okay, that will remain unhybridized, and that is gonna take part in formation of pi bond. This will take part in pi bond formation. I'll show you now. So let's say that we have a CC double bond. Okay, and I'm using ethene as a small example here. One of those bonds is sigma, the other one is pi. Okay, so we are saying that carbon is donating 3 electrons in the covalent bonds, just like that. Okay, those are the ones used to make the sigma bonds. So let's assume those are the sigma bonds. And then hydrogen is donating 1. So let's describe formation of sigma bond here with the hybridization of carbon. So we know that these electrons are sp2s. See, they are sp2s from this hybridization. I'm discussing this. They are sp2s. They are those 3 red dots on each carbon. So those combine with a 1s from a hydrogen. So hydrogen will give the 1s electron because hydrogen has atomic number 1. So the type of bond that you get in between here will be an S from the hydrogen and then sp2 from the carbon, and it's a sigma head-head overlap. That will be the same thing for this sigma bond when those 2 electrons combine, S sp2 and then S sp2 and then S sp2. However, this one right here is between 2 carbons, and those 2 red electrons came from sp2 hybridized carbon. This sigma bond is sp2. Now what about the pi? How is the pi formed? By, this electron right here is unhybridized and it's on 1 carbon. So assume you have another carbon having this entire representation. That too will have its own. So these 2 unhybridized electrons, they're in the unhybridized p orbital, and when these p orbitals do side-side overlap, that's how you're gonna get the pi. So when they come real close, they will overlap and then you get a pi orbital. In between here, remember, you have the sp2 sigma bond, and you also have the sigma bond here to the hydrogen. You have a sigma bond to the hydrogen. You have a sigma bond to the sp2 sigma bond to the hydrogen, sp2 sigma bond to the hydrogen. But on the top, you'll have the pi, that is side-side overlap. Let's discuss sp hybridization. Sp hybridization on carbon. We're still going to promote an electron upstairs, but only one of those p's will participate in hybridization. So you'll get sp, then you're left with 2 unhybridized p orbitals that are going to take part in formation of 2 pi bonds in the case of making a triple bond. So let's assume that what is in between there is a sigma. Let's assume that, and let's assume these 2 are pi's. So those 2 pi's will come from 2 carbons, bringing each 2 unhybridized electrons in unhybridized p orbital. Okay, so sp, those are 2 electron domains. So let's discuss what happens in the case of ethine. Ethine is an alkyne. I'm showing the triple bond. This is a classic example to show you hybridization. You have 1 sigma bond and a triple bond. Those are 2 electron domains. We could predict sp as done in a previous lecture. Remember, I said that one electron domain is a single bond, 1 double bond, or a triple bond, or a lone pair. So you see how you have a single bond and a triple bond. So you have 2 electron domains. So the possible hybridization would be sp for both of these carbons. Bond angle 180, molecular geometry linear, we discussed that in a different lecture. But let's discuss hybridization in this case. So we are taking that this carbon is bringing, for the sigma bond, it's bringing 2 electrons. Okay, the hybridized one, this is also bringing 2 electrons from the sp-sp. of the other carbon. So you have two carbons, each of those has this entire representation with two sp electrons. Those can be used in making the sigma bond head-head overlap. The hydrogen, as usual, is bringing one electron. Okay, so we are left to account for these pi bonds. Okay, so remember here that bond is sp from carbon, S from hydrogen. This bond here again is made by sp, and both of them are sigma bonds formed from head-head overlap. And then we also have this sigma bond right in there. That one will be sp from the two carbons. So what about the pi's? Now remember that we do have these guys here that are not hybridized. So I'm just going to focus on just those that are not hybridized, okay? So there are two on each carbon. So assume that these are on their p and hybridized orbital. Each carbon comes with two of them, so now I'm working on one from each carbon. When these meet up, you're going to get a pi bond. Now assume this one and this one is a second of this p orbital of each carbon. Okay, they have to be parallel to make a pi bond. So assume these ones also meet up, you get another pi bond. In between here we have the sp sigma bond. So if I'm to translate this, then I will get a pi bond, a sigma bond, and a pi bond. See, that's how this triple bond comes to be formed using hybrid orbitals. So again, when the black pi and hybridized p orbitals overlap, you get that. When the blue overlap, you get this. And then the red overlaps by making an sigma bond using sp. That is the case on how to understand hybridizations in carbon. See you in the next lesson.